All right, guys. So we are starting chapter 6. All right, and chapter 6 is all about polygons. Okay. So we've actually already talked about the first two terms we have in our vocab. All right. And we are going to continue, we are going to give other descriptions within these as well. Okay. But we're going to start with the term polygon. So polygon is a simple closed figure made up entirely of line segments. Okay. So this phrase right here, made up entirely of line segments, this is where that no curves rule comes in, all right? Because if you guys remember our discussions before, all right, polygons can't have curves, okay? So because it's made up entirely of line segments, all right, there has to be no curves, okay? Couple other things that we've talked about in the past, all right? We've talked about convex versus concave, okay? That's coming all the way back to chapter 1. Remember convex, actually I think concave is probably the easier one to describe. So if you guys quickly remember, this figure right here would be considered concave, okay? Because the definition says that if you put a line extending, all right, through one of those side lengths, remember it can't pass through the interior. So that's concave, okay? Convex is the opposite of that, where it's saying that if you continue any of the sides, all right, within the shape, that none of those sides, all right, would pass through the interior, okay? The other descriptor that we've talked about as well is regular versus irregular, okay? And we talked about this in chapter 1, but we also talked about it in chapter 4, all right, where regular means equilateral and equiangular. All right, so equilateral and equiangular. Okay. All right, so that's all about polygon. All right, now the next term is the diagonals of a polygon. And what that is it's a segment connecting non-adjacent vertices, okay? So if we look at, all right, this example right below it, it says draw the diagonals in for the following polygons, okay? So if we look at this first figure, okay, obviously it's a triangle because it has 3 sides, all right? But if I'm asking you guys to draw, all right, any of the diagonals within the triangle, you would notice that it's impossible, all right? Because all the vertices are adjacent, which means that there aren't any non-adjacent vertices, which means you can't draw the diagonals. So for a 3-sided figure, it's not going to have any diagonals, 0, okay? Now, if we look at the next figure, all right, this obviously has 4 sides, okay? And when we describe the number of diagonals, it's how many we can draw from one vertex. Not all of them in all right, from every single vertex, how many can you draw from one vertex, okay? So for example, if I look at vertex D, how many diagonals can I draw from that one vertex? And the only one that I could draw would be connecting D to F, all right? So there would be 1 diagonal there, okay? Now, in the next figure, all right, this is 5 sides. This is a pentagon, okay? And in a 5-sided figure, let's look at vertex H, okay? How many diagonals can we draw from vertex H? We can draw 2 of them, all right? So 2 diagonals from vertex H. And remember, it's just how many you can draw from one vertex. That's the descriptor for the number of diagonals, okay? Now, for our last one, so for 6 sides, all right, let's take a look at P, okay? I can draw P to N, P to M, and P to R, all right? So this is going to have 3, all right, diagonals. So if you take a look at, all right, the pattern here, if you have a 3-sided figure, 0 diagonals can be drawn. All right, 4, 1 diagonal can be drawn. 5 sides, 2 diagonals. And for 6 sides, 3 diagonals. You should be able to come up with a pattern, all right? And that pattern is that it's the number of sides minus 3 is going to represent the number of diagonals, okay? So the number of diagonals is equal to the number of sides, which we're going to use n to represent that, minus 3. So if I asked you, how many diagonals does a 25-sided figure have, you could just do 25 minus 3 and tell me, well, it has 22 diagonals, okay? Okay, so our next term here is the polygon interior angle sum theorem, all right? And it starts off with the sum of the interior angles of a convex polygon, okay? So a couple things, all right? Sum means we're going to add them up, okay? Interior angles means the angles inside of the polygon, all right? Has to be convex, and there's a formula for this, all right? So the sum of the interior angles of a convex polygon is, all right, it's n minus 2 times 180, okay? Let's, though, real quick, state n, all right, equals the number of sides. Okay? All right, so this formula is going to help you figure out, all right, what do the interior angles of any polygon have to add up to, all right? So, for example, if I wanted to find out the sum of the interior angles, all right, and we're assuming that these are convex, okay? So a pentagon has 5 sides, all right? So if I wanted to figure out the sum of the interior angles of a pentagon, I would do 5 minus 2 times 180. And using order of operations, I'd have to do 5 minus 2 first, obviously, all right, which is 3 times 180, all right? And if you multiply those together, you would get 540 degrees, okay? Let's try the next one. So a 21-agon means it has 21 sides, okay? So we would do 21 minus 2 times 180. All right, 21 minus 2 is 19 times 180. All right, and then if we quickly do that, all right, I don't have my calculator, 19 times 180 gives me 3,420 degrees. Okay? All right, we're going to pause there. All right, come back and we'll start at example 2.